I'm now planning to give you an introduction to the area of digital signal processing, the kind of processing that can be used for the treatment of signals coming from sensors, because those signals are very often polluted with noise, different kinds of noise sources. And very much of the kind of digital signal processing I'm going to talk about now is related to improving the signal to noise ratio, the relation between the amount of signal and the amount of noise, or simply improving the SNR of the measurement itself by applying methods that can kind of separate the noise from the signal. The outline of my talk today will be about the model for stochastic processes and stochastic signals that are used to model non-deterministic signals and non-deterministic behavior. The expected value and variance, white noise, mean value computation and signal to noise ratio, oscilloscopes using mean value computation, autocorrelation function for white noise, autocorrelation and its linearity property, and how we can use autocorrelation to improve signal to noise ratio of a measurement, cross correlation in the end. What we see here is a schematics of a stochastic process model. This is an ensemble omega, that has three realizations, in this case theta 1 to theta 3, where each realization is a time continuous deterministic function, and then there is a certain probability of occurrence for each one of these functions. So a time continuous stochastic process x of theta and t is a rule for each realization theta that belongs to the process ensemble omega, and unambiguously determines a deterministic function x of theta and t of the continuous variable t. And every realization is then a function with an assigned probability of occurrence. The set of realizations omega is called the process ensemble, as I said before. And if we fix the time to tk, t equal to tk, then we get the stochastic variable x of theta tk, where the realizations theta is a free variable. So if we fix the time to t equal to tk, then what we get is a stochastic variable out of this process. So this is explaining the basic of a stochastic process model and its relation to a stochastic variable. Could be good to know. And stochastic processes and stochastic variables are often used to model noisy signals. That's why we pay attention to this. This is a deterministic signal, a sine wave signal that is polluted with noise. And we need to treat this signal then as a stochastic process. We cannot predict exactly its correct values at all times because of the noise. But if we know its probability density function PDF, or its cumulative density function CDF at time t, then we can compute the probability for the signal having a value within a certain range of values. So what is actually meant here is that at any time point it is not possible to compute or determine exactly its value, but if we define a range of values, then it's possible to compute the probability of the signal to have a value within that range. The probability density function is used to describe the probability for a signal to have a certain value, for having a certain value within a certain range, and for all values. So for all values between a and b in this case, and for each one of the values, then there is an assigned probability. And this is a homogeneous distribution, which means that all the possible values that can occur will all have the same probability, constant probability. On the other hand, we see here on the right side a Gaussian distribution that looks like a clock shape, where we approaches infinity or minus infinity, the probability is very low, and then we have an increasing, slowly increasing probability of occurrence for the values. And where the center is with the highest probability of occurrence, that is that is modeled as the parameter of μ. I will explain more later on what μ is actually meant. The cumulative distribution CDF is computed according to this formula, so that we integrate the PDF from minus infinity to the value of x. So it means that we are summing up all the possible probabilities of having all the values from minus infinity up to the value of x. And from this it follows a very important property, that limits for the cumulative distribution function CDF when x approaches infinity must be equal to 1, because then we are actually summing up all the probabilities for all the possible values that can occur, and the sum of all probabilities must be equal to 1, 100%. The Gaussian distribution, the PDF for the Gaussian distribution is defined according to this formula that is also shown here in this graph, where sigma is a measure of the width of this distribution, and the value of μ is a measure of the position of the highest probability, the center here, the distribution. The expected value, väntevärde in Swedish, is an expected outcome of an experiment where its probability density function PDF is known. And then the expected value is computed as an integral, where we have the value that we are analyzing and the probability from the probability density function f of x. And we are integrating over all the values and for all the probabilities from minus infinity to infinity, and then we get an expected value of the outcome. And this can be interpreted as that you're computing kind of a center of gravity of that distribution. The traditional way of computing the mean value for an experiment is equal to its expected value, where its PDF is approximated from the outcome, which means that you can estimate the PDF from an histogram, and from that histogram you can compute the expected value, and that will be the corresponding to the mean value. Important properties of the expected value is that the expected value of a function of a stochastic variable x is equal to the integral including the function g of the variable, the stochastic variable x, times the PDF of x, and then we compute the integral. So then we have the expected value of a constant a times the stochastic variable x is equal to the constant a times the expected value of the stochastic variable x, where a then is a constant. And we have the expected value of the stochastic variable x plus the stochastic variable y is equal to expected value of x plus the expected value of y. And then we have the linearity combination of those two. So the expected value of a times x plus b times y is equal to a times the expected value of x plus b times the expected value of y, where a and b are both constants. Then we come to a more tricky one here in the end, a tricky rule. The expected value of x times the expected value of y is equal to the expected value of x times the expected value of y only if x and y are two statistically independent variables, which means that those two variables, they both behave in an undeterministic way, but also behaves undeterministic without any kind of relation in between each other. The variance is a measure of the variation around the mean value mu, and is defined as the variance of x is equal to the expected value of the stochastic variable's distance to its mean value mu, and we square this distance, and then from this function we compute the expected value. So this is the definition of the variance. And from this follows a number of important properties also. So the variance of the stochastic variable x is equal to the expected value of x squared minus the mean value mu in square. So this is actually the total power of the signal minus the square of the mean value. We can continue with the expected value of the variance of this stochastic variable x plus the stochastic variable of y is equal to the variance of x plus the variance of y. If x and y are statistically independent variables, and only if. The variance of a constant a times x is equal to the square of that constant times the variance of x, and a is then a constant. And then the variance of x is equal to sigma square, where sigma is the standard deviation of the variable x. All these rules for computation of expected value and variance can come very handy to learn and know. I'm now going to use them for the evaluation of signal-noise ratio from mean value computation, and how we can use mean value computation to improve the signal-noise ratio. So basically we are taking a number of data samples, put it into a data set, and on this data set we compute the mean value, and I will be able to show how this mean value computation can improve the relation between the signal and the noise. But I think firstly we need to start with the definition of something called white noise. This is a picture of noise, a non-deterministic signal. And white noise can be defined such that there is no correlation between two different values adjacent in time. So meaning if you take two values that are very close to each other in time, those two values are statistically independent from each other. We can continue then with a computation of mean value from a stochastic signal x, and we take n number of samples, and each one of these samples can be considered as a new stochastic variable, because you can think of it that we are repeating this mean value computation over and over in time, and then you evaluate in the end what will be the corresponding relation between the signal and the noise for the new variable y if we do this. And this new signal that we create, new stochastic signal, is computed out of n number of samples from the stochastic variable x. So we start with evaluating the expected value for this new variable y. Mu y is equal to the expected value of this formulation, being the formulation, the computation of the new variable y. And then the sum of the expected values are equal to the expected values of each one of these variables divided by the constant n. So we have n times the expected value of x, because we can be sure that the expected value for x1 and the expected value for x2 and the expected value for xn, they will all be the same as the expected value for x. And then we have like n times the expected value for x divided by n, which will be the expected value for x equal to mu x. So what we have concluded here is that the expected value for the new variable y will be equal to the expected value of the variable x. We can continue with the variance of this new variable y being sigma square of y equal to the variance of this expression. And now the variance of the sum of all of these stochastic variables is equal to the sum of the variance of each one of those stochastic variables, assuming that there is no correlation in between these two samples. And this is true because we are assuming that we have a signal that is polluted with white noise, which is a statistically independent samples, according to our definition for white noise. And then the constant we need to treat when we break it outside the variance computation. We need to have the square of this constant n square. And the variance of the variable x1 should be the same as the variance for x2 and the same for xn being the variance of x. So that's why we can rewrite this one as the n times the variance of x divided by n square. This will be the variance of x divided by n and equal to sigma square of x divided by n. So what we actually have said here is that the variance of y is equal to sigma square of x divided by n. So we are reducing the variance of y with a factor of n compared to the variable of x. And now we will continue on the next slide, because the signal to noise ratio is defined as SNR equal to the mean value divided by sigma. And SNR for the signal y computed as the mean value then becomes SNR for y is equal to mu y divided by sigma y. And mu y we have computed before that it is equal to mu x. And we have said that sigma y, the variance of y, is sigma y in square, is then the same as sigma x in square divided by n. And to get the sigma y instead of sigma y in square, we need to use the square root. And this is equal then to the square root of n times mu x divided by sigma x. And mu x divided by sigma x must then be the SNR of x. So this is equal to the square root of n times the SNR of x. So what we are saying here is that the SNR of the new signal y is equal to the square root of n times the SNR of x. So we are actually improving the SNR. And we are thus able to improve the SNR by a factor of square root of n by computing the mean value from n measured values. This is the conclusion from this exercise. Yeah, this was a set of equations and a theoretical development. But then how can we actually make use of this mean value calculation and the improvement of the SNR in theory if we apply it on an instrument for measuring a noisy signal, such as an oscilloscope that can be used to view a periodic waveform? We can have a look at these diagrams. It's a sinus waveform that is polluted with noise, and we have two sets of data samples where you have the equal amount of data samples in each one of these data sets. And the question is like how we can then compute the mean value and make use of the mean value computation to show this sinus waveform with reduced amount of noise, or even close to without any noise at all, how it is possible. So this is an example of where we have been using 16 of these data sets, not only 2 data sets. 16 of these data sets, and at each point of the in the corresponding data sets, then we are using these 16 values for the computation of mean value exactly in that point. So there will be a large number of mean values, and the result will look like this, where you can obviously see that the amount of noise in each point where we have computed mean values will be reduced according to the theory that we described before. And here is another example of using 256 of these data sets. And the whole idea is that you have an oscilloscope that can start to trigger on the same point all the time. Then it is possible to in a short time range you can acquire lots of data samples, or I mean lots of data sets, and in this case 256 sets. So the mean value computation from several data sets are used here to improve the signal to noise ratio for the measurement. And it is for the measurement I should emphasize this, that you cannot this way use mean value computation in the instrument to actually improve the signal to noise ratio for the signal, but you can improve it for the measurement by visualizing only the signal without the noise. But on the other hand, then this method, it will not work for really low signal to noise ratios because of the oscilloscope, that the triggering circuit must be able to accurately find the starting point for the data sets. Of course, there could be situations when the signal is very, very weak, and it is also polluted with noise and completely hidden in noise. So question is then, how can you actually detect and measure this signal if the oscilloscope is not capable of triggering on that signal because it's so weak and hidden in noise? If you look at this diagram here, here is a weak signal hidden in noise. It's a weak sinus waveform, and there is no way that you can, just by viewing this graph, say that there is a sinus waveform here. And it is extremely weak. This signal to noise ratio here is minus 30 decibel, which means that the noise is, the power of the noise is like 1000 times higher than the signal power. So, I mean, the oscilloscope, there is no way it's going to be able to trigger. So, how can we then create a situation where we can utilize the mean value computation if the oscilloscope cannot trigger? The frequency transform and the amplitude spectrum of the frequency transform, the behavior of this one is such that it is not dependent on the phase, and the phase is describing where the waveform actually starts, how it is delayed in relation to the origin. So the behavior of the frequency transform, where the frequency transform is actually complex worth on its output, and then you are computing on these complex worth samples in the frequency domain. You are computing the amplitude spectrum as the absolute value, and then you are computing the argument as the angle, the amount of delay, how the waveform actually is positioned. So you can utilize the fact that the amplitude spectrum is independent of the phase. Thus, it will not be dependent on where the oscilloscope trigger. We can allow the oscilloscope to trigger just randomly whenever it can start and end the data set whenever it is possible, and use that kind of data for computation of the amplitude spectrum. This is an example of the same signal that we saw on the previous slide. We have computed the amplitude spectrum on 512 samples in the data domain, and then after the discrete Fourier transform, then we will also have a spectrum divider on 512 frequencies, and it's computed on this data set on 512 samples. So if it is independent of the phase and where the trigger actually starts, then it means that we can do the same way as for the oscilloscope when it was triggering on every point here in this data set. If we acquire a number of these data sets and compute the amplitude spectrum, then we can use those data sets to compute the mean value at every frequency. And this is what we can see here on the right side. So we have been using then 16 of these data sets, 16 of these amplitude spectrums for the computation of the mean value. And now we can clearly see that there is a signal here that is significant compared to the available noise that we now can see. So we have been able to improve the signal to noise ratio for the measurement in this case using the amplitude spectrum and mean value computation. Here is an example of where we have been using 1024 data sets. So it means like 1024 amplitude spectrums, each one containing 512 frequencies. And now, I mean, the signal is the dominant one, and you can hardly notice that there is a noise background. Yeah, so this seems to be a very efficient way, even if there is no way you can detect the signal and see the signal in the using the oscilloscope because of its hidden completely in noise with very low signal noise ratio. Still, if you apply the amplitude spectrum computation and mean value computation, then it is possible to detect the signal, even if it is very, very weak. Isn't it fantastic? It's like magic, I think. The autocorrelation function is a way of measuring the statistical dependency for a signal and its time-shifted copy. I think you can imagine if you think about any kind of signal and then you are looking into two data samples that are close in time, and the closer they are in time, then of course it must be reasonable that they are like more statistical dependent. But the further away you go from between those samples in time, then the less likely it is that those data points are statistical dependent. And this is what we are going to measure with the autocorrelation function. Have a look at these definitions for the autocorrelation function. For an analog energy signal, it is defined as the integral of t, the time t, and we are assigning a difference between those two time points that we are evaluating the correlation, and the distance between those data points are tau, and we are multiplying the point at xt times with xt plus tau, and we are integrating this for all the time points from minus infinity to infinity, having the same space in between those pair of time points. And for an analog power signal, it is defined almost equally, except that we are now integrating between a time point 0 and t, and dividing with the period of t. For a time discrete energy signal, it is equally, but then we are using the index number of n and xn plus k, and k is now the number of samples that we are using as distance space in between these two pair of points that we are analyzing the correlation between. And the same goes for time discrete power signal, but now we are also dividing with the period of n number of samples. If a stochastic process is known, then the autocorrelation function can alternatively be defined as, for the analog power signal, as the expected value of two stochastic variables that come from the fact that when we are fixing the time for a stochastic process, what we get is a stochastic variable. And two of those are x of t and x of t plus tau, where tau is then the time shift between the time points when we are fixing the stochastic process. And we are computing the expected value. For a time discrete power signal, we have the similar definition, except that now we have k that is defining the difference in number of samples. The expected value of x of n times x of n plus k. And for the autocorrelation function, if tau is equal to 0, meaning that there is no time difference between the points that we analyze, then the autocorrelation function will be equal to the expected value of x of t multiplied with x of t. And this is the expected value of x squared, which we know as the total mean power. And this is equal to the variance of x plus the mean value in square. The autocorrelation function for tau equal to 0 is proportional to and is defined as the total mean power for the signal. This because of that we can analyze the autocorrelation function for tau equal to 0 for this power signal. 0 to t, which where t is the period of the power signal, and we are dividing with t, and we are integrating xt multiplied with xt plus 0, meaning xt squared, and we can recognize this as the power integral. So let me now remind you about the definition of white noise. It was like two data samples adjacent in time or completely statistically independent. And from this definition we can develop and analyze how the autocorrelation function will look like for white noise. And we will divide this analysis in two cases. Firstly, tau is separate from 0, and in the second case tau is equal to 0. And when tau is separate from 0, then it will be like the expected value for x of t times x of t plus tau. And since these two samples, according to the definition of white noise, are statistically independent, then we can rewrite it as the expected value of x of t times the expected value of x of t plus tau. And both these expected values will be evaluated as mu. And in the end we have the result of mu squared for the autocorrelation function whenever tau is separate from 0. And when it is equal to 0, then according to the development of from previous slide, we will get the total mean power. And we can make a simple drawing or diagram of the corresponding autocorrelation function. That will be a delta spike for tau equal to 0. And let's say that the mean value for the noise is equal to 0, then for all the other values of tau we will have a 0 value for the autocorrelation function. So the autocorrelation function for white noise with 0 mean value is a small data spike for tau equal to 0, and with its total area corresponding to the noise mean power p. There is also an interesting linearity property for the autocorrelation function that we can make use of when we are analyzing like sinus waveform that is polluted with noise. So the autocorrelation function for two stochastic variables that are completely statistically independent, the autocorrelation function for x plus y is equal to the autocorrelation function for x plus the autocorrelation function for y, assuming that those two variables are statistically independent, as we said. And we will come back to using this linearity property later on. If we now continue with computing the autocorrelation function for a sinus signal x of t equal to sinus of t. And we'll do this by evaluating the integral according to the definition for the autocorrelation function of a power signal over the interval of t, dividing this integral with t. And we have sinus of t times sinus of t plus tau. So it's a product of two sinus waveforms that we can rewrite as cosine. And then it will be easier to find the primitive function for this integral, and we can evaluate it for the result of a half cosine of tau. So what we can expect then, if we compute the autocorrelation function of a sinus waveform, is that we get a cosine waveform on the evaluation of the autocorrelation. Suppose now that we are analyzing a sinus waveform that is completely polluted with white noise. Here is a sinus waveform with reasonable amount of signal to noise ratio. And now we can think of how should this autocorrelation function look like if we also are assuming this linearity property, and assuming that the noise is completely statistically independent from the sinus waveform, which is a reasonable assumption. Then we should be able to add this cosine waveform with the delta waveform that we concluded earlier, that the delta waveform, the delta function, was the result of autocorrelation function for the white noise. So let's have a look on the analysis on next slide. This is a MATLAB simulation of a noisy waveform, of the noisy waveform that we saw on previous slide. And now we are getting a delta spike for tau is equal to 0, and then we will get a cosine waveform for the representation of the sinus waveform. So here we have clearly separated the signal represented as the cosine waveform from the noise represented as a delta spike. And then it is possible also to further separate the noise from the signal by computing the mean value on the autocorrelation function for a number of data sets. In this example, we have been analyzing 256 data sets, being the autocorrelation from the noisy signal on previous slide. And now we can see this as a clear cosine waveform with the delta spike here for tau equal to 0. And keep in mind also then that the autocorrelation function is in the same way as the amplitude spectrum for the Fourier analysis. It is independent of the trigger, the phase. So an oscilloscope that samples these data does not need to be able to trigger. It can trigger randomly on the data. As last part of this video presentation, I was planning to introduce you into the area of radar and cross-correlation, explain cross-correlation from the application of radar. And radar is a transmitter, a radio transmitter that sends out a radio wave, and we are measuring the time it takes from the station to an object and to be reflected on the object and back to the receiver again, and the receiver is usually located somewhere close to the transmitting antenna. And we are measuring the time of flight, the propagation time it takes from the transmitter to the object and back to the receiver again, as a measure of the distance from the radio station. You can have a look at this principal sketch here, where you have the transmitter and you have the receiver, and the transmitter is sending out a radio wave that is reflected on the object and reflected back to the receiver. And we are measuring the time of flight, which is the propagation time it takes for the transmission to hit the object, and the propagation time for the echo to reach the receiver antenna. Here on the next slide, I have made a simple MATLAB simulation, and you can imagine that we are sending out a certain kind of waveform at some point in time. And at the same time as we are doing the transmission, we are also monitoring the receiving antenna for the reflection. And the reflection is coming back some milliseconds later in time. We will have the echo signal back to the antenna. And the time difference here can be approximated to about like 55 milliseconds. We can see this quite easily here in the diagram. And let's assume now that we are recording both the transmitted signal and we are recording the received signal. Then we have the possibility to make a shift of minus 55 milliseconds for the received signal. And then we are analyzing the statistical dependent. If we are looking into those two windows and looking at this unshifted received signal and the transmitted signal, there is very low correlation between those two signals. But on the other hand, if you are analyzing the signal that is time shifted minus 55 milliseconds, then the correlation between this signal and this signal will be rather high, even though there is also noise present here. But still, it will be much higher than compared to this unshifted signal. And the evaluation of the cross-correlation function looks a little bit like similar to the autocorrelation, except that now we are dealing with two stochastic variables, x and y. And we have the time shift, the lag variable tau. We are evaluating a sample x of t of the first stochastic variable, and then y of t plus tau on the second stochastic variable. And we are evaluating this for all the time variables t from minus infinity to infinity. And then we can make a plot of the lag time tau on one axis and then the cross correlation on the other axis. And then we can see that if we have a lag of about minus 55 milliseconds, then we will have an increased response, which indicate that this is the position where we have the reflection from the antenna, and a lag time, meaning a time of flight of 55 milliseconds. So this was the application of radar and the use of cross correlation. This video presentation has been focused a lot on the impact of noise on sensor signals. We defined something that we call white noise, and we have also been looking into different kinds of methods for improving the signal-to-noise ratio for measurement. Mean value computation, and how we can improve the signal-to-noise ratio by mean value computation directly on an oscilloscope output. Mean value computation of the amplitude spectrum, and mean value computation on the autocorrelation function. In the end, we were also discussing the use of cross correlation to measure the time difference between two signals. Well, I just want to thank you for joining me on this interesting topic, and hey, good luck with your noisy measurements.